Assalamu alaikum. Welcome to your lecture in Principles of Computer Networks. In this lecture, we will discuss data link layer. In the lecture, we will cover data link layer design issues, error correction and detection, and elementary data link protocols. The link layer has multiple design issues. We will discuss the service provided by the link layer to the network layer, framing, error control, and flow control. The basic functions of the data link layer is to provide a well-defined service interface to the network layer through which it can obtain the services provided by the data link layer. It also has to deal with transmission errors, detecting them and correcting them if possible. It has also need to regulate the flow of data between a fast sender and a slow receiver so that the slow receiver won't be swamped by data. The data link layer encapsulates the network packet into a data link layer frame, dealing with the packet along with its header as pure data, total disregard of the header of the packet contents. Adding a header and a trailer, a header containing control information like the packet length and so, and the trailer contains a checksum for the receiver to be sure that the data has reached the receiver error-free. There are two types of communication: the actual communication that happens through the data link layer, the physical layer, onto the physical communication channel, wired or wireless, and virtual, where the two data link layers assume they are talking to each other directly. In this lecture, we will adapt the virtual communication model. The data link layer provides three types of services to the network layer: connectionless service with no acknowledgement, connection-less services with acknowledgements, and connection-oriented services with acknowledgements. The unacknowledged connectionless services has no connection to be established before sending data. The source sends the frames to the destination and does not expect any acknowledgement or any confirmation that the data has reached the destination, and there is no error check made whatsoever. It's appropriate for channels with low bit error rate like fiber optics, and it's appropriate for real-time data like Ethernet and multimedia data. Acknowledged connection services is services with no connection established, and each frame is sent to the destination will be acknowledged with an acknowledgement sent to the source, and it's useful for unreliable channels such as Wi-Fi. Unacknowledged connection-oriented services is the most sophisticated type of services provided by the data link layer, where it actually confirms that the data was sent and received in the same order, free of error, and was received only once. The other issue of the data link layer design is how to frame data. This might seem like an easy task, but it's a rather complicated one. The data link layer obtained a raw data in forms of bits from the physical layer and sends it as packets to the network layer. That means it needs to format some kind of data unit in order to understand where the data begins, where it ends, and what are the contents of the data. The data link layer transforms unreliable channel into reliable by adding flow control. The data link layer breaks the bit stream into discrete frames and compute checksum for each frame to make sure that the data has arrived without errors. And the frame arrives as a destination if the checksum is correct, then the frame is accepted. Otherwise, the frame is discarded. Whether an acknowledgement will be sent back to the sender to resend the frame. How to break the data into frames? That's the question. There are 4 methods to break data into frames: byte count, flag bytes, and flag bits. Lastly, physical layer encoding violation. Byte count is a very simple, straightforward technique where the header will contain a field saying how many bytes are there in the frame. As we can see in the figure below, the frame headers contains the frame length, and the receiver will simply read the header, count the bytes, and then at the end of the bytes, it will assume that the next byte is the header for the next frame. But what if an error occurred? In this example, a 5 has been flipped to 7. The data link layer at the receiver will assume that the frame length is 7, and it will actually interfere with the next frame. This will be an error that will continue. It might be discovered when the checksum does not equal the checksum that was sent, but neither the sender nor the receiver can know where the error occurred in order to retransmit the data. A way to work around this is using flag bytes with byte stuffing. That means a flag byte is added at the beginning and the end of each frame. These flag bytes indicates the beginning and the end of the frame, and each consecutive flag bytes means a new frame has begun and the old frame has ended. The question here, what if the flag bytes occurred in the data? And it might happen. That's to say, a byte with the same value of the flag byte occurred in the data. The receiver then will be confused and will assume that this is the end of the frame, where it's not the end of the frame. For this, we introduce a skip byte that is inserted before each accidental flag byte within the data, marking it as not being a flag byte. It can happen that the skip byte itself can occur in the data, and this when a skip byte will be preceded with a skip byte. As we shall see in the example here, the frame has 2 flags, one at the end and one at the beginning, determining the beginning and the end of the frame. But if the flag byte happens within data, a skip byte is introduced, and if the skip byte has occurred in data, another skip byte is introduced. In the third example, a flag byte and a skip byte has happened in the data, and each of them was stuffed by a skip byte, And in the last one, there 2 escape bytes happened in the data, and they were both stuffed by escape bytes. The data reaching the receiver will be destuffed, where all the escape bytes will be removed, and the data will go back to its original form. Stuffing can happen on bit level, where framing can also be done on bit level. The frames can contain an arbitrary number of bits. For example, here we have 5 consecutive ones as a bit flag. And when the sender sends the data to the receiver, it will look for the flag at the beginning and on the end of the frame. Bit stuffing happens when there are 5 consecutive ones in the data. So a 0 bit will be stuffed in the data to mark the flag bits from the ordinary data, as we can see in this example. Every 5 ones were stuffed with a 0, and at the receiver they were destuffed and the data went back to its original form. With both byte stuffing and bit stuffing, there are side effects that the length of the frame depends on the type of data it contains. If there is no flag bytes, a 100 bytes of data can be transmitted roughly on a 100 byte size frame. But if all data were flag bytes, then this will double, and the 100 bytes of data will be transmitted in 200 bytes of frame. Same could be said about bit stuffing, only it increases the size with a lesser percentage, 12.5%, because each byte is stuffed with 1 bit. To overcome this, we introduce physical layer coding violation. As we have discussed in the previous chapter, the physical layer introduced some redundant signals in order to avoid noises and to make sure that the data has reached the receiver as it should. For example, 4B5B line code sends 4 data bits on 5 signal bits to ensure sufficient bit transition. This means 16 out of 32 signal possibilities are not used. We can use these signal possibilities to indicate the beginning and the end of the frame. Usually, a combination of these methods are used. For example, on Ethernet, a preamble that contains a byte count is there, along with a delimiter to mark the end of the frame. So flags and byte counts are used. The other issue in designing a data link layer is error control. The data link layer has to ensure that a reliable frame delivery. Every frame should reach the destination free of error and in order. To provide this, there are 2 types of acknowledgements: positive acknowledgements and negative acknowledgements. There are all positive acknowledgements is when the frame reached the destination free of errors, and negative acknowledgements is when the frame reached destination errorless. This is on the receiver side. On the sender side, we will introduce timers that will actually be used to monitor if the acknowledgement has reached the receiver, the sender, or not. If the acknowledgement did not reach the sender in a certain amount of time, the timer will go off, causing the sender to resend the data. This can happen due to two cases. Case one, the frame itself has vanished and due to any noise and did not reach the receiver, so the receiver will not react in any way, not by sending an acknowledgement, negative or positive. And when the timer goes off, the sender will know that there is something wrong and resend the frame. The other possibility is the acknowledgement itself can be lost on its way from the receiver to the sender, and the same situation will happen. The timer will go off and the sender will resend the data. In this case, two frames will be received by the receiver, two identical frames will be received by the receiver, and that might cause a problem if it was forwarded to the network layer. To prevent this, we introduce sequencing. That's to say, every frame has a sequence number, and the receiver will receive frames in order. When a frame is duplicated, the receiver will find that it has the same sequence number of the frame it has already processed and will discard it. The last issue with the design of data link layer is the flow control. The question is, what do we do if a sender is trying to swamp a receiver? A fast sender is trying to swamp a slow receiver. An example for that, a smartphone asking data from a web server. A smartphone has modest capacity and the web server has a very huge capacity. So what shall we do? We will introduce flow control in order to stop sender from swamping the receiver with data. Flow control protocols has very well-defined rules about when the sender can send the data to the receiver. There are two approaches. The feedback-based flow control, this is used in data link layer, and the rate-based flow control, which is not suitable for data link layer. The feedback-based flow control is when the receiver sends feedback to the sender, telling the sender if it's okay to send data or not. The rate-based flow control is when the protocol itself has built-in mechanism that limits the rate at which the sender may transmit data without using feedback from the receiver. Last but not least, error detection and correction. An error when the data reach the receiver in a different format that it has been sent. Digital signals can suffer from noises during transmission, and this can introduce errors to the binary bits. A 1 can be flipped to 0, or a 0 can be flipped to 1. There are three types of error. Single bit error, where a single bit is damaged, is flipped, and that will cause the data to reach the destination corrupted. Multiple bits errors, when multiple bits are flipped simultaneously, and that will definitely cause the data to be errorless and reach the destination damaged. The multiple bit error is rather rare compared with the single bit error and the purse errors. The purse errors are when several consecutive bits are flipped mistakenly in digital transmission. It creates a burst error, and it can happen because of a data shrug or a high noise. And it Errors tend to happen in bursts rather than in bits. Error detection is the process of detecting when an error happens. Error detection has multiple methods, such as simple parity check, two-dimensional parity check, checksums, and cyclic redundancy check. When data is sent from the sender and the receiver, sometimes it needs to be both detected and corrected. Error correction ensures that the data is corrected and error-free. There are two types of error correction. Backward error correction. This is where the receiver sends a negative acknowledgement to the sender, asking the sender to retransmit the whole data again. And the forward error correction, this method, the receiver is the one who is responsible of correcting the errors. See you in the next part.